what about if we have a pipe that is closed in one end, like here, and open at the other end, like here? The displacement that's in red here should give us a node at the closed end. Pressure is going to be an antinode at the closed end. At the open end, pressure is going to have, like always, a node. And the displacement is going to be an antinode. Let's run this. So you notice there we have a node for the displacement function and an antinode for the pressure. Notice here that we have a node for the pressure, look at the color as well, and an antinode for the displacement. Pay attention to the molecules too. They don't move much here. Look at that air molecule, for example, that representation of the air molecule, and look at these instead. Now, this is the first mode. Frequency is 82 Hertz. Now we go to the second mode. The frequency is 247 Hertz. That's 3 times the fundamental frequency. Notice here that for the displacement, we added a node here. So we have one segment plus half a segment. Lambda over 4 plus lambda over 2. 3 lambda over 4 overall for the length of this air column. That's the way we find the wavelength. 3 lambda over 4 is equal to the length. And the frequency, as I mentioned before, is 3 times the fundamental frequency. You notice a node for the displacement at the closed end, an antinode for the pressure. The pressure is going to have one node in the middle here, not exactly the middle, but inside, and one node at the open end. Let's go to the third mode. Okay, the third mode, we added another node for the displacement and another node for the pressure. And you notice the frequency here is 412 Hertz. That's 5 times the fundamental frequency. Okay. So essentially, very much like when we have a string that's tied in one end and free in the other end. Again, we have pressure antinode at the closed end. So this is the closed end, and here this is the open end. If this represents pressure, first harmonic, and then we don't have a second harmonic, we have only odd harmonics. So this is our first overtone. The relationship between the various harmonics and the fundamental frequencies m times f, with m being an odd number, only odd m's. For the same m, we can find the wavelength as 4L over m. For example, here for m equal 1, that would be 4L. The length of this is lambda over 4. It's half of a segment. Here we have 3 lambda over 4. So here m is going to be a 3. For this one, m is going to be a 5, and so on. And again, we still have the wave equation that's always true.